March 25th, 1954, an important year in the automotive industry, Chrysler Corporation announced the development and successful road testing of the first American-built gas turbine engine in a production line automobile. This engine was a milestone in automotive power engineering. It overcame two of the major problems long associated with vehicular gas turbines: high fuel consumption and scorching exhaust fumes. The key was the development of a rotary heat exchanger which converted exhaust heat into a strong power boost with fuel economy. These tests were run in a 1954 production model Plymouth. They were the beginning of thousands of miles of road testing and resulted in a major breakthrough in turbine power. Almost a year later, in 1955, the same basic engine was traffic tested on the streets of Detroit. This was part of a continuing program in the search for improved performance. By 1956, engineers had set the stage for a major test, the first turbine-powered transcontinental run from New York to Los Angeles. A turbine-powered sedan, a production model in every other respect, made the historic 3,020-mile trip subject to constant evaluation of the engine's durability, acceleration, fuel economy, endurance, and operation under various climatic conditions. The engine performed beautifully, and 4 days later, the test car rolled into Los Angeles, marking another Chrysler first in the automotive record books. Guided by this performance data and experience obtained on the coast-to-coast run, Chrysler Engineering spent the following 2 years designing and developing a new, more advanced turbine engine. In December 1958, after thorough laboratory testing, this second-generation turbine engine made a 576-mile run from Detroit to New York in a test to verify the effects of the newly developed variable nozzle principle on economy and control. On this trip, the 1958 version showed that burner efficiency was improved almost to the point of ideal combustion, removing one of the most formidable remaining hurdles to successful automotive application. In the following months, another obstacle was eliminated when, through Chrysler metallurgical research, new materials were developed which contained plentiful and relatively inexpensive elements that could be made by conventional methods and still have excellent resistance to heat and oxidation even at extreme temperatures. Development on the turbine continued with one goal in mind: constant improvement. By December 1961, after more months of patient development, an improved third-generation turbine power plant, the CR-2A, was installed in a 1962 production line model, which made another 4-day cross-country trip. It encountered sub-zero weather with snowstorms and freezing rain, as well as scorching heat, at times bucking up to 40-mile-an-hour headwinds. The turbine lived up to and exceeded all expectations. Its fuel economy was consistently comparable with that of piston cars, which made the same trip. Over a decade of research and testing, modifying, redesigning, always improving, had evolved the most advanced, most practical gas turbine engine ever specifically designed for automobiles. The culmination of this sustained and dedicated effort was Chrysler Corporation's announcement in 1962 that the company planned to build 50 turbine-powered passenger cars for release to selected customers. This was to be done to obtain concrete evidence concerning public acceptance of this revolutionary type of automotive power plant. Years of research and testing had evolved a turbine engine that overcame the major problems when development began, a turbine that truly met all expectations. But now that this engineering achievement is here, perhaps it would be well to consider just what is a turbine.
What is a turbine? Actually, a turbine is a highly advanced use of one of man's oldest means for creating power to do work, the windmill. The windmill, as most of us know it, consists of a number of curved blades called vanes mounted on an axle. A breeze blowing against these vanes causes the windmill to turn and to supply power to do many kinds of jobs. As the wind increases, the windmill spins faster, provides more power. The turbine, acting as a controlled windmill, makes today's jet airplanes possible. But its use in a passenger automobile is substantially different. First, we'll lift the hood on the gas turbine car for a look at the engine. Now, looking down on the engine, we can, through the use of animation, get a clearer picture of how the turbine engine works. To perform efficiently the functions of an automotive power plant, Chrysler Corporation's gas turbine was designed with these main units: air compressor, combustion chamber, first turbine wheel for compressor drive, second turbine wheel for driving the car, regenerators or heat exchangers. The air compressor sucks in outside air and compresses or squeezes it to raise its pressure. Compressing the air raises its temperature to more than 425 degrees Fahrenheit. This compressed hot air flows through the regenerator, where it is further heated to more than 1,000 degrees Fahrenheit, and then into the combustion chamber into which the fuel is sprayed. The fuel is ignited by a single spark plug, is burned, and further raises the air temperature to 1,700 degrees. Then this now red-hot tornado of air or gas forces its way past the blades of the first turbine, whose job it is to turn the air compressor, regenerators, oil pump, fuel control, and other necessary accessories to make your car function. The hot gas then turns the second turbine, which is connected to the rear wheels to drive your car. But that isn't the whole story of the turbine engine's operation. Two other major elements make the gas turbine engine practical for use in a passenger car. After leaving the combustion chamber and passing through the two turbine wheels, there is a drop in the temperature of the gases as they flow to the exhaust. But the gases retain large amounts of heat which would be wasted if merely allowed to escape unhindered through the exhaust pipe to blister the paint of cars following. So a device for salvaging this heat is placed in the path of the outrushing gases. This is the famous Chrysler-originated rotary regenerator, which is basically a heat exchanger. To more easily understand the role of the regenerator, let us take a closer look. To do the job, the regenerators turn slowly, transferring heat energy from the exhaust gases through special heat transfer surfaces to the high-pressure cooler air being pushed by the compressor on its way to the burner. This eases the burner's job of raising the gas's temperature on their way to the turbines. This preheated air requires less fuel and permits the turbine to develop fuel economy comparable to a piston engine. In the Chrysler turbine, the air itself is turned by special curved blades called nozzle vanes. These vanes change their position to direct the stream of hot gas against the turbine blades at different angles, economy for cruising, or greater power for acceleration, or even a braking effect for slowing and stopping. In spite of the increased efficiency of the engine, the gas turbine is simplicity itself. It has only about 1/5 as many parts as the common piston engine. Because it is self-cooled, the turbine needs no radiator nor antifreeze. There are no timed events in the turbine engine, no need for a distributor nor a carburetor. There are no tappets, no valves, finally, no pistons rushing up and down in their individual cylinders. In the turbine engine, you have a smoothly efficient operating system which burns almost any available fuel: gasoline, kerosene, diesel fuel, furnace oil, jet fuel. You have no temperature starting difficulties, no engine warm-up period necessary.
The place is the 5-mile test oval at the Chrysler Proving Grounds. The event, performance checks of the production model gas turbine car. This is the culmination of tens of thousands of miles in road experience and improved design, resulting in a gas turbine engine specifically adapted to the exacting requirements of today's motorist. These are the trials before this new car is released for limited customer evaluation. production models will have the rear view mirror mounted in a holder on the windshield. "75 miles an hour and running steady in a smooth, vibrationless, trouble-free ride. Passing rugged endurance and power requirements with ease. But the Turbine car is not a special car designed for limited types of performance. This is a car for people, for doctors, housewives, school teachers, average people with average as well as extreme driving requirements. This is a thoroughly tested, thoroughly practical car to meet customer driving needs. Here is a car with power engineered for safe and ready acceleration when needed on the highway. The now perfected heat exchanger ensures excellent efficiency from the engine and a cool, clean exhaust even at sustained high-speed driving. Now the Turbine car moves out of the oval onto the twisting, tortuous side roads at the proving ground. Roads scientifically planned to tax the strength, maneuverability, and control of any car. The turbine-powered automobile passes these grueling tests. Here is a car designed to be free from costly maintenance worries, periodic oil changes, and seasonal tune-ups. Here is full power potential for instant acceleration and outstanding climbing ability. Through the action of the variable nozzles, the driver is assured the same control he can get in the best conventional passenger car, even on the steepest grades. Here indeed is an engineering breakthrough worthy of the painstaking experimentation, constant testing, designing, and redesigning that went into it. The light, compact, reliable, easy to maintain, economical to operate Chrysler Automotive gas turbine engine. Now the first 50 production model turbine-powered automobiles are nearing release to selected but typical motorists who will drive them under a wide variety of conditions. The motoring requirements of these drivers will vary across a broad spectrum. The tremendous potential of the turbine to satisfy power plant needs for propelling automobiles more smoothly and dependably than ever before opens the possibility of an exciting new chapter in the history of motoring and gives the automobile a running start in the jet age.